In this video, we're going to look at how definite integrals appear very naturally when we're modeling physical systems. It's pretty common in the sciences to be able to estimate, compute, or measure the rate of change of something. One example is actually likely in your pocket right now. It's an accelerometer built into your cell phone. What we'd like to be able to do very frequently is work from that rate of change, say an acceleration, backwards to velocity or say to position or change in position. The general formulation of that is taking a rate of change, say of position, rate of change would be velocity, and then finding the net change of that same underlying variable, so finding the net change in position given the rate of change of position. It turns out that integration is going to be our gateway for doing that. Let's take a look at an example. You've got water flowing into or out of a tank at a rate given by 200 minus 10t liters per minute. So that's a rate of change of volume. We add the codicil that positive values indicate the flow is into the tank, so negative values would be flow out of the tank. This is the kind of thing we could measure with a flow meter. What we might be then interested in is how much water is actually in the tank. So how does the volume itself change over time? Let's consider the first 30 minutes of this transaction, of this rate being in place, and ask yourself, how would I go from this rate of change, liters per minute, to the change in the volume of water over the first half hour or first 30 minutes of filling? This will be challenging the first time through, but take a look at the options here and see if one of them makes the most sense to you at this point. We'll check in a minute. All right, so we know that R of t is 200 minus 10t, and a key ingredient of that is liters per minute. So if we were to sketch this out for a second, R of t and t, and we have the units of liters per minute and minutes, what would we do with this graph? Turns out it's a linear decay graph, that doesn't really matter. What we care about is how we would go from this to a change in volume. Well, a change in volume is a number of liters. So imagine shading out the region underneath this graph. That area, in quotes, would have units of liters per minute times minutes. And that points to an integral being what we want to calculate for the change in volume. If we wanted to break it down even more into the kind of expressions we've seen already, we would imagine building a sum of delta t's times r of t. And that is a real indication of how we're going to build our integral. So we would have r of t times delta t as a sum. And then when we transform that into an integral, that just means using finer and finer rectangles, then we could identify that just by looking down the list. I should see r of t. There's one with r of t. These two are potentials here. I need r of t exactly like it was written out, 200 minus 10t. And then when we change to the integral notation, that delta t becomes a dt. So that makes b the answer we're looking for. This transformation of the idea of a sum, we have a rate in liters per minute times a small time interval in minutes. That gives us liters, and then we're going to add that up over a whole time interval. That's exactly what the notation of the integral does for us. So that would equal the change in volume in the tank. As a follow-up to that, having a delta t and a dt in the same expression is usually a red flag. The purpose of changing from summation notation to the integral notation is that we're letting delta t, or we're letting the number of intervals head to infinity, and that changes a fixed interval size of delta t and lets it become a tinier infinitesimal amount. That's usually how people think about this, a tiny width, but it's still there as an expression or as a component in the integral. All right. With that in mind, let's do an estimate of what this value would be. To estimate that value, let's start with the exact. Integral from 0 to 30 of 200 minus 10t times dt. And we're actually going to take a step back and say that's approximately equal to a sum of 200 minus 10 t sub I kind of things here, delta t. What are the values we're talking about here? Well, if we are using 3 intervals, and we are doing that over 30 minutes, then the natural time breaks are 0, 10, 20, and 30 minutes. That points to a delta t of 10, and so we can go straight to our sum. We would have the rate at time 0, if we're using the left-hand sum. We'd have the rate at 0, we'll do it explicitly here, times delta t, plus the rate at 10, the next time point, times delta t, plus the rate at 20, times delta t, confirming our units again, liters per minute, times minutes. That's going to give us liters when we're done. And then we can fill in the values. Our rate function is just this part here, r of t. So literally we say, hey, what was the rate of flow at time 0? Well, it was 200 minus 0. That was 200. I'm going to take this delta t and move it to the end, so we don't have to keep multiplying by it. And we'll just have the rate values inside these parentheses. What was the rate after 10 minutes? Well, it's 200 minus 10 times 10, that's 100, so 200 minus 100 is still positive 100. And last but not least, on the third interval, we would use the 20 time point. 200 minus 20 times 10 is 200. That actually adds up to 0. And again, we have that all of these are liters per minute. All of these are in minutes. And in fact, we can be a little more explicit about the delta t now. That was 10 minutes for each interval. And we end up with 300 times 10, which would be 3,000, and the final liter units come out at the end. Having calculated that value, it's important to follow up and say, what is it actually telling us? Does this information tell you the actual volume in the tank after 30 minutes? And the answer to that is absolutely not. This is the change in volume, which is not the same as the actual volume, just like saying I drove 10 kilometers today doesn't tell you where I am or where I started. And again, that makes sense. If all we are told is how quickly water's coming in, it doesn't tell us where we started. It doesn't tell us how much water was in there to begin with. Then this would be the net change relative to that amount. Let's take a look at a second example. In developmental physiology, one function that's of interest is the height of a child as they grow. Here we're going to record it in centimeters at time t in years. We're also told that the child is 120 centimeters tall at age 10. And we're asked here, how would you represent the amount the child grew between t equals 10 and t equals 18 years? So basically pre-puberty to post-puberty. There will be a formulation of that. Take a look at the options down here and see if you can identify which integral here captures that amount of growth over that time frame. Pause the video and we'll check in a moment. One of the best guides for these kinds of calculations, again, is units. If the height is just centimeters, what you can do is write that in for each of the times you see h, and remember dt is actually capturing a small time interval, a delta t, and so it has the natural units of whatever time variable we're using here, so years. And h prime of t, well, if you have h as a function of t, the derivative, going back to earlier work, is centimeters per year, and then the dt would be in years. If we consider those options, and we imagine what we're trying to calculate here, the amount the child grew would be in centimeters. No question at all. It's just a height difference. And so these units here don't make any sense. Centimeters times years, I don't know what those represent in this scenario. However, these formulations down here do give us centimeters. So if we knew how quickly the child was growing, that's what this h prime of t is, the rate of growth, then an integral would get us back from the rate to the actual change in height. Having reduced the options to C and D here, we notice the only difference is whether we add the 120 centimeters, which is their height at age 10. But think back to what we saw earlier in the previous example. If we integrate a rate of growth, we get a change in height. That's what we mean by the net change being equal to the integral. If all we're told is how quickly they're growing, then when we add how quickly they're growing times the lead units of time, we find out the change in their height. And this is what we were actually asked for in this scenario. How much did the child grow by between 10 and 18 years? This integral here. This is a perfectly interesting value to compute. It's the change in height plus the initial height, their initial heightness, tallness. And if we capture those two together, then that's going to equal the height at age 18. Very interesting property, just not what the question was asking for, which was the amount they grew by, not how tall are they. And having that distinction clear in your mind is important as we work with integrals.